Okay, yeah, we talked about the untyped lambda calculus, simply typed lambda calculus. And let's see. Yeah, the point of this is that, well, what we will eventually do, I said we're going to do proofs next. We're actually going to not do that quite yet because there's other things I want to talk about first that motivated a little more, I think. But anyway, the point of this will eventually be that once we have this more formal definition for our type systems, we can prove things about them. So instead of just having some language that's vaguely specified, like a lot of programming languages are, we'll have something formally specified that we can prove it does certain things, the programs terminate or do whatever, and that the type system is reasonable and all these things. If you recall, the simply typed lambda calculus was way too weak for our purposes, and that you can't really write a whole lot of interesting programs using just that. I mean, in some sense, you can't write any programs using just that because you need to add some sort of primitive types like Booleans or something to get non-infinite types. But yeah, even just that, you just have these just like Booleans and then functions on Booleans and functions on functions on Booleans, and it's all kind of pointless. But we can add a bunch of other small extensions to get interesting behavior. So first I'm just going to go back over really quickly what we had last time. So at the top we have the syntax. We have types, which are represented by tau. This is not working. What is going on? Well, maybe I'll not be able to draw separate with my mouse, but we'll see what happens. So my mouse can't draw either.
I think you need to select a brush, yeah.
With like this. Okay, so I can draw with my mouse now. I still can't draw with the actual tablet I have though, which is much more convenient. Oh, there we go. Okay, anyway. Yeah, so syntax is, here we have types represented by tau and expressions represented by E. For expression, we have values true and false. We have variables, lambda abstractions, and application. Here are the reduction rules down here. It's an awful line. Anyway, we have this congruence reduction rule that says if we're doing an application and the thing on the left is not already a function, we can just kind of keep evaluating it until it is. Once it is a function, then we can apply the function by substituting in this argument e prime for x in the body e. And we can also alpha convert, which we didn't talk too much about, I guess, but you can change the name of these bound variables as long as it doesn't cause the free variable capture. Basically, as long as it doesn't cause issues. So as long as I don't use y and e, basically, this is safe. There's other ways to define it that are slightly more elegant, but this works fine. Yeah, hopefully you remember some of this. And then we have the type rules again. This is just all on one page. So we have this Boolean rule that says if something is like constant true or false, then we can give it the type bool. We have variables. So if x is a type tau in the environment, then we can type check x with the type tau. If f is a function from tau1 to tau2 and x is a value or expression, whatever, yeah, I guess it should probably be e, not x, of type tau1, then f of x is of type tau2. And then finally, if given that x has type tau1, we can type check e as an expression of type tau2, then lambda x dot e has type tau1 to tau2. It's a function from tau1s to tau2s. And this is saying basically, when I'm evaluating e, I'm going to know what x is, so I'm just going to assume that x is whatever type I say here. Yeah, any questions about that before we move on? Okay. So the next things, we're going to talk about a couple different small extensions to simply type Lambda calculus to make it into more or less a real programming language. Still missing a lot of things that you would want in a programming language, but much better. So I'm going to write these extensions like this. So this is triple dot saying everything I had before plus these new things. So first we're going to do natural numbers, then we'll do product types, which are like pairs, and sum types, which are, if you use Haskell, it's like either or just the bar thing. And if you don't use Haskell, it's kind of like subclasses of a parent class. There's just like multiple ways to make a value of this type, but we'll talk about that in more depth later. Yeah, so we're going to extend the syntax. So now we have a type of natural numbers. I'm just using this symbol because that's the standard natural number set sign. I guess people sometimes write nat when they're doing programming, but I'm going to write that because I have LaTeX. And then we have a new kind of expression, which is n. N is just like a number, like 0 or 1 or whatever. Oh, that's fun. And then we can also add the natural numbers. You could add subtraction and stuff, but it's going to work exactly the same for the type checking purposes. So I'm not going to do that. Okay. So we're clear on what we're doing. Okay, cool. Oh, that's a nice thumbs up. I didn't know you could do that. Yeah, so one note here is, so these are going to be the rules for evaluating the natural number expressions. One thing I'm going to note is this is how I'm going to write like real natural number addition. So we have this syntactic expression that means add these two expressions together. And then we have the actual function that adds two numbers together. So I'm going to write that one with this subscript n. Hopefully that is clearer. You could also think of it as being some like hardware addition implementation thing or whatever. But just this represents, this isn't a syntactic construct. This is actually whatever, n plus n is. So we have these two congruence rules again. Again, just like in before, when we wanted to evaluate the first expression until we got a function so we could apply it, here we want to evaluate both sides until we have numbers so that we can add them. So these two rules are exactly the same, just one does the left-hand side, the L1, and one does the right-hand side. So these rules are, they're very boring, but you do technically need them. There are ways to reduce how many of these you need, but this is, I think, conceptually simpler to just write them. Hopefully those make sense. And then for the addition rule, all we say is once we do know the actual numbers, so n is like 0 and 2, then it evaluates 2, 2. Maybe 0 wasn't a good choice, but oh well. So yeah, we just evaluate both of the operands, whatever the word for adding is, addend, I think, until they're both numbers, and then we evaluate that to their sum. And that's all we need to do for the type or the dynamic rules. And for the type rules, it is very simple. All I'm just saying is if n is like something in the set of natural numbers, like 0, 1, 2, 3, whatever, then we can say that n has type natural number. We don't care about the environment because it's just a constant. And then for addition, all we need to check is that the two operands E1 and E2 have the type natural numbers, and then their sum will also be a natural number. Okay, this is meant to be a fairly straightforward example, so I hope it is. The next ones are going to be more complicated, so if you have questions, let me know. Okay. Also, if you have questions about something that I move forwards on, just feel free to stop me and ask. Any questions in the chat? Okay, I can't see the chat for some reason.
There are no questions in the chat, don't worry.
Okay, thank you. Anyway, yeah, so now we're gonna talk about something more interesting, hopefully. So basically the most common way to make new types is to make product types. These have lots of different names in different languages. At the most basic level, they're just like tuples in Python or, std pair or whatever in C++ and all that. But also things like records or structs or even classes in some sense. If you're just considering the data portion are product types. Those just have names for every one of the fields. And doing records instead of product types is basically the same thing, except you have the names instead of just like left and right. So I'm just going to do this because this is simpler. Yeah, so now we have one new kind of types, or one new sort of types, which is tau times tau. It's called a product type for a reason that we'll talk about later. But intuitively, it's because you have sort of as many things as the product of the number of things in both of the sides. So if you do like a pair of Boolean, right, there's like 4 kinds or 4 values in the type bool, sorry, times bool, because you have true, false, false, true, 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 false, false, etc. Anyway, we make a pair by writing just like a regular ordered pair. E sub L means the left projection, so you take the left thing out of the pair, and E sub R means the right projection. You take the right thing out of the pair. I would have done like first and second, but this is, I like this. But you can think of the left projection as being like the first function and the right projection as being the second function. So let's see. Yeah, so these rules down here are like the standard congruence rules where you just evaluate both sides of the pair, which we don't technically need in our language because our language doesn't have any side effects. So we can actually just only have these top 2 rules and just project out whichever thing we want. If you were in a language like Python or something, you would need these 2 rules down here because when you evaluate E1 or E2, you may change something about the environment. And if you just throw that away, the program will behave super weirdly. But we don't have that. So I put these here for completeness, but we don't technically need them. All we really need to do is when you see a pair and then this left projection, you just take the left thing. And when you see a pair and the right projection, you take the right thing. And yeah. Okay. So here's some opportunity for audience participation, so to speak. So we want to type check pairs. So we have E1, comma E2 is of type tau1 times tau2. What should be on top to make sure that this is a reasonable well-typed expression?
Maybe if like E1 is of type tau1 and E2 is of type tau2.
Yeah, but okay, yeah.
There should be
Just for fun, what should?
Oh, I was gonna say it can be either or, right? So E1 can be T1 and E2 can be T2, or E2 can be T1 and E1 can be T2, right? So there's like 2 options.
In this particular way we're defining the product types, the E1 has to be type tau1 and E2 has to be type tau2. You could do it sort of that way. That would be more like a record style of doing it, I think. Or maybe like an unordered pair maybe, but yeah. So actually, no, whatever, this is fine. I mean, I assume this is what you mean. Colin. Okay. So yes, that will work. And then maybe I should have done the other ones too. But anyway, so yeah, this is how you type check the pair, and then you type check the projections just by. So if E is a pair of tau1 and tau2, then the left projection is just type tau1. And if E is a pair of tau1 and tau2 again, then the right projection is of type tau2. And now you can write programs that have pairs. Pairs are very useful, obviously, in building up more complicated data types. And we are one step closer to having a real programming language. So that's product types. Any questions? Okay. So some types are like a little less common. They've been modeled when you have multiple ways to construct a value, like alternatives. They're kind of like enums in like C or C++ or Java, etc., where there's like a set number of values of whatever type, except they can be more complicated. It's not just like, if you have like an enum for like days of the week, it's not just, Monday, Tuesday, Wednesday. You can have like Monday and then like a value attached to it too. So we're just going to deal with like these binary sums of 2 different types. So basically I'm saying if E is of type tau1 plus tau2, that basically means E is either of type tau1 or it's of type tau2. So you could do literally like E could be of either type. An easier way to do it that requires less like non-determinism and stuff is using is essentially tagging it with when it's the left one, as in tau1, or when it's the right one, which is tau2. And these are called in L and in R, which is short for left injection and right injection. So it's saying basically it maps values of type tau1 into this sum type, and it's a injection. So if you give it two different values, you'll get two different values in the sum type. That doesn't matter so much as just basically it tags the expressions with which side of the sum they are. And then the way that you use the sum types is you do a pattern match or switch case sort of thing on them. You say, well, if it's the left one, then it evaluates to whatever this expression is. And if it's the right one, it evaluates to whatever that expression is. So we will now do the standard thing. We have the syntax, then we'll do the evaluation rules or dynamics, and then we'll do the type checking / statics. So these rules are much longer.
Wait,
Yes.
question?
Yes.
Regarding the last expression thing, could you explain that like a little bit more?
Yeah.
Case E and stuff.
Yeah. Actually, maybe I'll go to this page. Maybe it will make things clearer, but I'll try to explain. So basically, this case thing means you evaluate E until you figure out if it's the left type or the right type. And then if it's a left type, you evaluate using the first branch. You pass this value in for X in the first branch. And if it's the second type, then you pass whatever value in for Y in the second branch. So for example, if you have, I mean, one kind of sum type is like an optional. So you so like the left one would be none, like no value or null or something. And then the right value would be some value. So if you have like a optional list, for example, then none is no list. I guess we wouldn't use it for list, but none is no list and some would be some actual list. Or if you think of it as a pointer, then none represents a null pointer and some represents a pointer that actually points to something. So then doing a switch case on that is saying, if it's null, then do E1, and if it's not null, do E2. Does that help?
Yeah, okay, makes sense.
Okay. Yeah, so as usual, we have this congruence rule where we just evaluate this expression until we get it into a form of either the left injection or right injection. And once we know which one it is, then we can just substitute. So if it's the left one, we substitute E for X, that's the first branch. And if it's the right one, we substitute E for Y in the second branch. So again, we could keep evaluating this expression 2 all the way down and then substitute, but because we don't have side effects, it doesn't matter. Yeah. So yeah, this is, I mean, in some sense, it's like a fancier if statement. Like you can, like if you were to do sort of the simplest possible sum type, you get like a bool basically. It's like either you only care if it's left or right, you actually care what the value is. And then this is just an if statement. So you're saying, if it's the left one, you can say that's false, then you do this thing. And if it's the right one, then it's true, and you do the other thing. I guess if statements are usually true first and then false second, but yeah, that's fine. Does that make sense? Okay. Well, we'll see. Yeah, so let's talk about the type rules first and then the notes on top perhaps. So on a basic level, you can construct a value of type tau1 plus tau2 using either value of tau1, type tau1, or a value of type tau2. And if you have a value of type tau1, you use the left constructor. And if you use a value of type tau2, you use the right constructor. And they both end up with this tau1 plus tau2 type. You'll notice you don't actually have to, tau1 can be anything. It's just here. You can pick literally anything you want, and same thing for tau2 in this version. which causes some minor issues, but it's not so bad, and you can fix it, as I'll talk about in a second. And then the type rule for case is a little bit more complicated, but hopefully it makes sense. It's basically like a combination of an if statement and function application in some sense. All you have to do is you have to check that E has type tau1 plus tau2, and then type check each one of the branches. So we want the branches to return the same thing because we want to be able to statically know what the type of this case expression will be. So we can't have one return like a Boolean and one return a natural number, because then we wouldn't know how to use the whole case expression. So we require that they evaluate to the same type, and they're both allowed to use their respective parameters. So the first branch can use X, assuming that it's of type tau1, and the second branch can use Y, assuming it's of type tau2, because we'll only call the first branch when E is a left injection, and we'll only call the second branch when E is a right injection, or use the right injection. So yeah, let me briefly return to this point up here, which is that, so as I said before, this tau2 can be anything, which means that if you're writing a program that type checks it, you sort of have to guess what it will be, which is, if you have some sort of like type inference, that's fine. If you don't, then you do really, you kind of have to guess, or like non-deterministically like backtrack maybe once you figure out what it's supposed to be, which is a little awkward. So everything you can do is you can annotate it by saying what the type of the other thing is. So this is the left injection, but I'm going to write what the type of the right side is, so that there's only one way to type check it. And then this rule would look like this. And now it's not, and now it is deterministic, because I can no longer choose tau2 to be whatever I want. Tau2 has to be whatever was written, the subscript of this. Does that make sense? Okay. Okay. So that was the extensions I wanted to talk about. Those are pretty common extensions you can add to most of Lambda calculuses. But as you'll see, as we get more powerful type systems, we don't actually need these things. We don't need to modify the type system to get them. The language will become expressive enough to define these things on their own, which is quite nice because you don't have to add any more rules. Although it is maybe conceptually more complicated because you have to do some encoding of the structures, but we'll see that if we end up having time, or maybe next week or whatever. Yeah, so I want to briefly talk about algebraic data types. So you notice these things are called sum types and product types, because they correspond in some sense to sums and products, which means you can add types together, you can multiply types together, which gives you some sort of algebraic structure on types, which is intellectually entertaining, I find, even if it's not usually directly applicable. So yeah, don't worry about what a semi-ring is unless you know what it is, and then that's what this basically forms. But basically, I'm going to talk about doing computations with types, and where we're going to say the two types are equal is not the normal definition of equal, like they're equal if they're exactly the same thing, but they're equal if they're isomorphic. So what that means is you can define two functions, so some function f from tau to sigma and some function g from sigma to tau, such that when you compose them, you get the identity function. So they're each other's inverse. And if you can do this, then we say the two types are the same because they essentially have the same values. You can just rename them to the other values by using these functions. So what these functions essentially do is rename things. And that's the important thing. So here's an example. So bool is of course true or false, and maybe is, I'll define it. Maybe in Haskell is defined to be either nothing or just a, where a is, so you can have a maybe of ints, you can maybe of bools, maybe list, etc. In this case, I'm using maybe of this. This is how you write the unit type in Haskell. The unit type is the type that only has one value, which is called unit. So like bool has two values, true and false. Unit has just one type, and it's called unit, which is written confusingly with these brackets or parentheses, I guess because it's like a tuple with nothing in it, and there's only one of those. I think that's the analogy that's supposed to be going on here. I don't think it's really a great choice, but such is life. So here I'm defining a function that maps Booleans to maybe unit. So I'm just arbitrarily picking true maps to just unit and false maps to nothing. And then the inverse of that, G, is basically the same thing. So true mapped to just unit here, and now just unit maps to true here. And here false map to nothing, and here nothing maps to false. So these types basically are the same thing because I can just like rename things back and forth. Another way, or another example of this would be, for example, strings and lists of characters. So you can map each string to a list of characters and each character into a list of strings. And if you do this in a reasonable way, then mapping a string into a list of characters and then back into a string should give you the same string you started out with. So we would say that those two types are also isomorphic in this sense. Hopefully that makes sense.
Go ahead.
Yeah, okay. I was wondering, could you also define it as there's a bijective function between the elements of the two types?
Yes. The only catch is that not all types, I mean, essentially that's what this is. The only catch is that not all types are like sets. So bijection is usually just the word used for like functions on sets. That.
Oh, I see. Okay.
But it's basically just, yeah, it's basically that. It's just a generalization of that idea. Is there another question?
Oh, I was just going to ask if you're going to show some other, like a more complex example.
I will show examples of things.
Sure.
I'm happy to do more type isomorphic examples if that's what you want. Is that what you mean, or?
Yeah, I guess because I mean, it makes sense that like Boolean and maybe because there's only like two values, like that's a really easy conversion, but maybe something more complex would help me understand it.
Mm-hmm. Yeah. I mean, yeah. So I mean, for any type that only has finite and many things, you can just choose some arbitrary mapping like this and do it. Yeah. So the strings and lists of characters. Another thing you could do is, yeah. So you could map integer. Oh, also, this is the symbol for when two types are isomorphic. I guess I didn't write that anywhere, but that's the symbol. So integer could do bool integer, which is sort of a weird one maybe. But so what you can do is you can map each number into, so let's see. You would do, or one of the ways to do it. So the first thing is going to be if n is even, I guess like even n, and the second thing will be n over 2, I think. Yeah, I think this, sorry, I didn't actually plan this one out, but I think this will work. So you divide n by 2, it's even, so that's fine. And then, wait, sorry. If n is even, then you do this. If even n, and sorry for writing over it, true n over 2, else if n is odd, then you can do false n over 2. I guess if this like rounds down, maybe then it works. And this gives you mapping into pairs of Booleans and integers. And then the mapping back is if it's true, then you multiply the number by 2. And if it's false, then you multiply the number by 2 and add 1. And then if you compose these two functions, you'll get identity functions both ways. So those two types will also be isomorphic. Does that make sense?
Interesting. Okay, nice.
Yeah.
Wait, this only works for like if your integer is like infinite, right? Like not.
Right. Yeah. Yeah. This only works for like real integers. Yeah.
Okay.
Yeah. Yeah. In a Haskell integer is supposed to be like the arbitrary precision, like real integers. Obviously, they're limited by like the size of your computer, but like, yeah, you're right. And then int is the like 32-bit or 64-bit integer. Okay. I can try and come up with more, but they're always gonna be like math examples like this, basically. There's other ones you can do, but well, anyway. So basically, I'm going to define this new type. So I'm going to write the unit type 1 because I think that's actually a much better way to write it because it's a value that has one value. And I'm going to define this thing finite n. This is just a finite type that has n things in it. Because like I said before, it doesn't really matter what the things are called. It just matters that there are n of them when it's finite. And then, so bool is basically 2. So bool times bool equals finite type of 4 elements, or 2 times 2 equals 4, basically. You can write this out explicitly if you want, like mapping false false to 0, false true to 1, and true false to 2, and true true to 3. I mean, you can pick any mapping you want, but that's the sort of binary one. You also have 1 plus 1 is 2, which is what we did on the previous slide, basically. And yeah, so those are sort of easy examples, I guess. I mean, very, very vague examples because I didn't actually write up the isomorphisms, but I hope you can imagine. And then there's another algebraic thing you can do, which is construct an exponential type. This is basically just a type of functions. Again, this is sort of inspired by if you have a finite set, how many elements there would be in this type. So if you have like a set that has, well, let's say you have bool. If you have bool functions from booleans to booleans, there's 4 of them because you can map true to true or false. You can map false to true or false, and each one of those choices gives you a different function. So the number of eraser is too big. Okay. So if you look at how many functions there are from bool to bool, you'll get 4, which is sort of the inspiration behind this. And then if you look at, more, I don't know, bool to the bool times bool. So this will be like 2 to the 4, which is, what is that, 16? Yeah. And that's the corresponds to the number of functions that take a pair of booleans and give you 1 boolean back, which is also the number of like Boolean binary operations like and, or, etc. There's 16 different possible operations. Most of them aren't very useful, but and or are obviously quite useful, and XOR, etc. So there's 16 of those, and this type will be isomorphic to the to any type with 16 elements in it, in particular this finite type with 16 elements. And this is an explicit isomorphism showing you that 1 to the bool is equal to 1. So 1 to the 2 equals 1. It's actually true that 1 to anything will give you 1. You basically do the exact same thing. Here, the way I defined it, so the function from bool to unit, which is 1, I take some argument and then I ignore it and I just return unit. And then my function from unit to this type of functions, this isn't even the right thing. It should be this, but it gives you the same thing, essentially. Or f of, well, it doesn't matter, f of anything, because I just ignore the argument and return unit. Anyway, sorry. Yeah, so, and then mapping back from unit to the type of functions from booleans to unit is you just return this function that always returns unit, because that's the only function actually you can have from any type into unit. Because it is, well, that's not important. If you know category theory, it's because it's the terminal object in this category. And if you don't, then it's because there's only one value. So you can't actually return anything else. Yeah, does that make sense?
Wait, a question for the like addition operator and how you define like fin n. Is the addition here still like our like sum type thing, like different options for the value of the type?
Yeah.
And how does that work for like, wait, are these like ones, like different values?
No, they're all the same one. Yeah. So this is something we didn't technically define this. I mean, you could define it as like 1 plus 1, which we did define, plus 1, plus 1, like etc. So if you want to like actually write out a value of this type, it would like, if you want to like do like this, like pick this one, it would be like some horrendous like in L like unit thing. But I don't really want to deal with that, you know, especially if there's like a ton of, especially if it's like 16 or something, right? So
Okay.
but yeah,
wait.
you're right.
So then the point of this type is just to have like exactly n elements,
Yeah.
or like n different values it can take.
Yeah.
on.
Yeah.
Okay.
Yeah. I mean, yeah, the other thing I'll point out is this definition here is not really something you can define in our language as we have it right now. I'm just sort of relying on your intuition of repeat something n times. But you need a much more powerful language to actually define this in the language. And you need like dependent types, I guess. But that's not really important. As long as it makes sense to you that I'm just defining like an infinite family of types, one for each natural number. And the point is, as exactly as you said, that just has n elements in it. You know, like I could very well write, you know, fin2 is bool if I wanted to. And this is like bool times bool times bool times bool, but this is easier. Okay, if that makes sense, I'm gonna do something that I just think is fun, but is not really very important. But it's a way to use like calculus with the data types and you end up with something sort of reasonable. So I'll just briefly talk about this and then we'll move on. So lists are kind of like this infinite sum type. So list of A's is like, so either unit representing an empty list, or one value of A, or 2 values of A, or 3 values of A, or 4 values of A, or et cetera, et cetera, et cetera. So in some sense, you could say list is this, I guess it should be isomorphic, this sum 0 to infinity of various products of A's. So I'm writing A to the 2 here to mean like A times A, like product types like we had before. And then A to the 3 is similar to the previous definition. A to the 3 is like this, and et cetera. So lists are kind of like this infinite sum. If you remember from, I don't even know math class teaches this, like algebra 2 or something, some of a geometric series, or some geometric series, geometric sequence is 1 over 1 minus r, where r is the ratio between the terms. Here our ratio is A, this type. So if we use this formula somewhat dubiously to solve this equation, we have list A equals 1 over 1 minus list A, which is a weird thing because I don't know what 1 minus A means necessarily in terms of types, or what 1 over some type means. But if we just sort of go with it, then, and we solve for, we sort of remove all the weird stuff, right? We solve for A, or list A, removing the minuses and the division, we get list A equals 1 plus A times list A, which is, in some sense, how lists are defined in Haskell. So list is either empty, nil, which corresponds to this one, or it's an A and more and another list of A's put together. So it's like a pair of A and a list of A. So I just think that's
Put that on your own?
Huh? No, I saw this somewhere and I was like, that's very entertaining, even though it's kind of nonsense. I hope you agree. Anyway.
Yeah. The lack of mathematical rigor is amusing.
Yes. Yeah, I think somebody tried to formalize like negative types at some point. I don't remember exactly how that went or if it's useful at all. But this is just pretending that doing this makes sense. Anyway, let's see. yes, I have one slide on this because it's sort of an important topic if you're interested in like proof assistance and that sort of thing. So one way that you can use type theory to help you check proofs is through this thing called a Curry-Howard isomorphism or correspondence. And so in the previous few slides, we were looking at these operations, sum types, product types as algebraic things. So computing things using or having certain laws like A times B will be isomorphic to B times A, and so on. We can view them in a different way as logic whole propositions. So here the product of A and B means, well, it means A and B, as in logically A and B. A plus B means A or B, and A to B, instead of being some exponential thing, means A implies B. And in this view, A is some proposition, and a term of type A is a proof of A. So if you want to encode this logical statement, if A implies B and B implies C, then A implies C, which hopefully makes logical sense to you. Then we rewrite this as this type. So a function from A to B and a function from B to C gives us a function from A to C. If you think about this sort of in programming terms, this sort of makes sense that this is a thing that you could implement, because if you had a function from A to B and you had a function from B to C, and then you want to write a function from A to C, all you have to do is given an A, produce a C. And to do that, all you have to do is use this first function to get a B and the second function to get a C. Here is this program written in the simple type Lambda calculus we've built up so far with some of the extensions we used, or just the product type extension, actually. So we take in this P, which represents a pair of these two functions. And we take in an X, which is the value of type A, and we need to build a value of type C, which I'll do just by composing the two functions in the pair. So the left function is this. This is the left function. This is the right function. So first I call the left function to get a value of type B, and then I call the right function to get a value of type C. So I guess, does it make sense to everyone why this term has this type up here?
Oh, wait, we can't see what you're pointing to.
Oh, you can't see the actual pointer? Okay. Does it make sense why, let's call this T. Does it make sense why T has that type?
Wait, I forgot how the syntax works here. Can you give a brief refresher?
Yeah, so you mean this part, or this part down here?
Yeah.
Yeah. Okay.
Like, how do I break this part and like read it?
Yeah, so the lambda, this is a lambda abstraction, starts with a lambda, so it's gonna be a function. Its argument is P. The type of P is this big thing here. And the return value is this second part. And the return value is also a function, right? Because we're gonna return a function from A to C. So we're returning another function, so lambda x. X has type A because we want the input type to be A. And then we want to return a value of type C. So this is the body of the function that we're returning here. And we return, we supply both functions in the pair to X in, I guess, the only way you really can, because X is type A. So we apply this first this left function from A to B. So P L, or left projection on P of X has type B, and the right projection of P on that has type C. Does that?
Okay. Yeah, I can see how everything goes together now.
Yeah. Yeah, I really thought that. Yeah, so the idea behind this is, yeah, so this term has this type, and because there's a term of this type, that means that this proposition, or this proposition is true. This is sort of a, I don't know what the word is, sort of a philosophical correspondence, not something like super rigorous. I mean, you can prove that this works, but I'm sort of asking you to take it on faith at the moment. Yeah. So the reason that this product corresponds to and is because to have a value of this product type, I must have values of the left side and the right side. And if we view terms as proofs, then having a value of the left side means I have a proof of the left side, and having a value of the right side means I have a proof of the right side. If I have both values, I have a proof of both of them. So I proved A and B. Maybe that, hopefully that makes sense. At any rate, like I said, this is just supposed to be a very quick thing about this, because I want to talk about this stuff in a lot more depth at some point. I don't know if it'll be next week or not, but talk about proof assistance, and most of them are based on this idea in much greater depth. So I will, oh, there's not much time. Okay. Well, anyway, so this is the thing that I was wanting to do next last week, which is talk about how you actually prove type safety for a language. And the way you usually do it is you split it up into two parts, two separate theorems. One of them is called progress, and the other one's called preservation. But the basic idea of proving type safety is that if the program type checks, then it should run and do something. In our case, the program will terminate because our type system is so weak, but that's obviously not always the case. But it does mean, if your program type checks, then it shouldn't get stuck. There shouldn't be at some point, there's just no rule to evaluate whatever situation you're in, because the type system is supposed to rule that out. And if the type system doesn't rule that out, then it doesn't really type check your program. You're sort of missing rules maybe, or something like that. So that's the broad idea behind type safety. And more specifically, progress is saying that, so you have E as some expression, closed expression, so there's no variables that are, or those only bound variables. You don't have any variables that are basically not defined. And if E is a closed expression and it's well typed, so this, I'm just going to read this as E is well typed, even though there's a lot more there, then either E is a value, meaning that we're done evaluating it. So it's this constant true, this constant false, or a lambda, that should be the type on it. I'm going to ignore all the extensions because, as you'll see, this is a very case-based thing, and I don't want to do like 6 more cases, which, yeah, you could. So either if E is well typed, then either E is a value, or there's some expression E prime such that we can evaluate to E prime. So we can keep going. And preservation says if E is well typed and E evaluates to E prime, then E prime is also well typed. And then the combination of these theorems sort of naturally gives you, if a term is well typed, then you can keep evaluating it until you get to a value. If you can prove both of these things, then your type system, in some sense, reasonably checks that your program runs in some way. Yeah, and then just this quick footnote that here I'm requiring that E and E prime, the thing that it steps to, have the exact same type. That works for us, but in some languages that doesn't work. For example, in Java, if you have some expression that returns, some parent class, and then you actually run that expression, you'll probably get some subclass instance. So the type will no longer be necessarily the parent type, but a subtype of the parent type. And there's other variations on how that works, but for us, it'll be the exact same type. Any questions about this setup before I do a couple of the cases? Okay. So, yes. Oh, yes, important thing, recall proof trees. So we're talking about all these type rules. This is the same proof tree I showed last time, but basically the point is that if a term is well typed, there will be some proof tree that looks vaguely like this, which proves that it's well typed. And this idea is going to be very important in the proof of the theorem, because the way that you prove these things is typically by induction on the proof tree. So you look, so this term is well typed, which means there must be some proof tree. You look at the proof tree and you say, basically, what was the last rule that was used to prove that this term is well typed? So in this case, it would be app. If I was just looking at this constant false, it would be bool. and so on. And then we'll use induction when we need to do something with the premises. So we'll say, because the proof tree that proves that one of the like sub expressions is well typed is smaller than ours, we can use the induction hypothesis to get the same statement, but for the or the same theorem up here, but for the sub expression. I'll talk about that in more depth in a second.
Reed, real quick, can you say why it's called progress?
Oh yeah, it's called progress because it's progress in the sense that you make more progress in the calculation. So if the term is well typed, then well either, so if E is a value, maybe I didn't mention this, value means that you're done computing. So either you're done computing or there's some other expression that you can step to, and that step is the making progress in the computation. So it's saying that, you know, if the type of term is well typed, you're either done or you can keep going, but there's never a point where you just can't do anything.
Okay, got it.
Yeah. And then preservation is called preservation because it's saying after you take a step, you like the type is preserved and that it's still well typed. Yeah, so yeah, we're gonna do induction on the derivation of E being well typed. So basically we need to do one case for every single rule in our type system, which is one of the reasons why you want to have fewer rules in your type system. Because we have like 4, it's going to be a little bit of a pain. If we had, you know, 12 or like 100 or something, then it would be much, much worse. So first case is bool. So maybe I'll go way back to the bool rule. So suppose we use this rule to prove that E is well typed. In that case, by definition, or by definition of this rule, that means that the expression must be in true or false, which means it is true or false. And in both of those cases, it's a value. So we fulfilled, this first. So we said either E is a value or we can keep evaluating it. In this case, E is a value. So then we're done with this case. Okay. The second case, if we use the var rule last, that would mean that E is a variable. So equals X for some variable X. It's just the way of saying that E is a variable. But then E is not closed because this variable can't be bound by anything because this is the whole expression. So that contradicts our premise that E is a closed expression. So we don't actually have to consider this case at all. Or we have to consider the case to say it's impossible, but we don't have to do anything else. Okay. There should not be a square here. We are not done. Okay. Anyway, so here is the longest case by far, which is the case for function application. So if the last rule that we use to prove that this expression is type safe is function application, that means that the expression must be function application. So E1, E2 for some expressions, E1 and E2. So because of the way the app rule works, for this expression to be well typed, we have to know that E1 has type tau1 to tau2 and E2 has type tau1, because that's just the premises of the rule. So if we use the rule to type check it, then the premises must be true. So we can assume that these two things are true, which is what inversion of the typing derivation means. I mean, technically I have to prove this, but I won't, because I think it's obvious in this case. So then by the induction hypothesis, so we know these two things are well typed, and we know that their proof trees are sub-proof trees of our bigger expression, right? Because they're sort of like on top of the line. So in that case, that means their proof trees are shorter, so we can use the induction hypothesis to get the same progress statement, but instead of E, we have like E1 or E2. So by this, well, we're just going to use the induction hypothesis on E1. We don't actually care about E2. So by the induction hypothesis, we know that E1 is either a value, so it's done being evaluated, or E1 evaluates to, or steps to E1 prime for some other expression E1. So here's two cases. with some more opportunity for audience participation. So if E1 is a value, then something. What is this something?
Then we're done.
Not quite.
Oh man, dang.
Yeah, because just this part is a value, but the whole thing.
Oh, right. Okay.
Yeah. So I'll give you a hint. So if E1 is a value, then E1 is going to be lambda x tau, or I guess I wrote tau once, I'll put tau here, dot E, I should use E something else, E double prime, I'm sorry. Then E1 is lambda x is tau 1 dot E double prime. And then, so E will not be a value, so we need to show that E evaluates to something. What will it evaluate to?
Wait, why does E1 have to be strictly a function here?
Oh, because we're in this app case, we know that E1 has the type of a function.
Oh.
And we know that, I mean, technically there's one other case you have to eliminate, which is that E1 is a variable. If E1 were a variable, this term wouldn't be closed, so that can't happen. So we know E1 has a function type, and we know that E1 is a value. The only values that have function types are lambda abstractions, because the other values are true and false, and those don't have a function type. So it must be lambda. Yeah. Yeah, there's a few steps, I guess, that go into this, but yeah. So what I'm saying is, so E1 is this lambda, which means that this whole expression looks like this. So that means that it evaluates to E double prime, substituting E2 for X. So this is, so because E evaluates to something, E evaluates to, let's call this E single prime. I don't think I used that yet. Okay. So then E evaluates to E prime. So that's it for this.
Yeah, so wait, then we get like that it E1, E2 evaluates to type tau 2. For the case that if E1 is a value, then we can say that E is of type tau 2.
Yes, it is. We don't actually have to prove that now, though. That's technically in preservation where you prove that.
Okay.
But it's true. Yeah. All we have to prove is that either E is a value or it evaluates to something. So we proved E evaluates to something, so we're good.
Oh, okay.
Yeah. And then the other case where E is not a value, or E1 is not a value, that means that E1, with this assumption, so E1 evaluates to E1 prime, which means by the congruence rule that E1, E2 evaluates to E1 prime, E2. So again, so if E is a value, then E evaluates to something. And if E is not a value, then E also evaluates to something. So in both cases, we can make progress. So we're good in this case. The app case, that is. Whoops. Whatever. The app case. And then in this last case, I'm just going to do it because it's like 3. So in this last case, if E is a lambda already, then E is a value, because lambdas are values. You can't evaluate them any farther, at least not in our system. So regardless of how the proof tree is built up, in all cases, we can prove the desired conclusion that either E is a value or it evaluates to some E prime. So we proved progress. We still need to prove preservation technically, but I'm not going to do that today. Actually, I don't think I have notes for that. Yeah, anyway. Hopefully this made sense. I don't plan to do a whole lot of these proofs because they're kind of tedious. but it is good to know how it works. If it doesn't make sense, feel free to ask. But I think we'll stop here for today. We'll go through my other 21 slides at some point. I want to briefly talk about what things we want to do next. So this was the second type theory week. We can do a third, fourth, fifth, sixth, et cetera, forever type theory weeks. But I want to see if people want to switch and do something else, or just more of this. So thoughts?
I think this is cool so far, and I have no idea what most of these are. So
Okay.
anything
Yeah,
goes, I think.
Yeah, so basically, yeah, I mean, well, the real question is, should we do type theory or not? And then if we do type theory, do you want to do more Lambda calculus functional type theory stuff? Or we could do, there's this thing called featherweight Java, which is like a small Java version or a small Java type system, which is interesting just because it's different from Lambda calculus. And there's lots of other things we could talk about too, obviously. What are you saying?
I was gonna say featherweight Java caught my eye. That might be a nice contrast once we've kind of reached a good point with the current stuff.
Mm-hmm. Yeah. Okay. Any other thoughts?
Recursive type seems like it'd be part of sort of the material we've already been discussing, though, right?
Yeah, I mean, it's definitely related, but it's not necessarily. I mean, you can do, I mean, even the next type system we're talking about, system F, you don't need recursive types in it. You can actually do a surprising amount without it. But it is useful for real programs. Okay. So unless there's any other feedback, I guess the plan will be, we'll talk about a little bit more of this Lambda calculus stuff. The other slides I plan to talk about today. I guess most of these are not. Yeah, okay. Anyway, for some of next week, and then we'll move on to featherweight Java, and then we'll see after that again where we want to go. Does that sound good?
Okay, yeah.
Sounds great.
Yep, sure.
Cool. Yeah, thanks everyone. I'll see you guys next week, hopefully.
See ya.
Okay.
Bye.